Okay, hello everyone. Welcome back to lecture 9 and 10. So I was revamping the lecture slides here, so it's more kind of current and up to date. So that's why it kind of took me a while to make this lecture, but now we're all ready to go. So here's chapter 6. So this is gases part 1. So this is chapter 6. So this chapter will probably take a couple weeks. So we actually won't finish a chapter per week. In this case, it'll probably take more than that because there's a lot of material to digest. Okay, so let's get started here. Okay, so we know gases are a huge part of our lives in terms of entertainment, parties, balloons, um, like the bouncy houses, fun times as a kid. So a lot of things we kind of enjoy as a when we were younger. A large part of that has to do with our understanding of how gases work and how molecules that form those gases. Okay. So, properties of gases, there's 3 properties you want to know. They're easy to compress, so you can compress air in a tire. They expand to fill their containers. If you open a scented candle, light a scented candle, it'll fill the room with a very unique aroma. And of course, this also applies to very unpleasant smells. So, when when you go when you go to the restroom, or just a natural process when we have too much gas built up in your bodies, it naturally wants to expel itself into the atmosphere. Okay, so gases can be both pleasant, unpleasant, and they can also be we'll see here used to do chemical reactions and where they can be somewhat dangerous as well. So a very common example of an application of gases is the internal combustion engine. Okay, so here we have an example of a 4-stroke engine, and it can be divided into 2 cycles. Here we intake some gas, we close, then the valve is closed, we compress the gas, and then that compression will generate energy in the form of kinetic energy. And so we compress, then that compression actually does work and transfers energy, and that will eventually cause a reaction in the spark plug, and that will convert the gas molecules into energy. So what that does is a combustion reaction, and the spark plug there causes a oxidation reaction, combustion reaction, and the gas molecules that are now expended, CO2 and usually water, they're emitted out into the atmosphere. So sometimes not all that, so the exhaust is pretty much CO2, some water vapor, but it's also some other elements in the air, like nitrogen, so nitrogen oxide, nitrogen dioxide. So that's one of the prime reasons is the cause of global warming or climate change. Pretty much is because the car, we're using energy, and that energy generates not so good byproducts, and that's what contributes to the overall haze in the air. You probably don't see it because it's not really transparent in the air because the sky still looks blue, but mostly molecules are pretty much colorless, so you actually don't see them. So they are actually causing an effect, but you actually don't see them. Okay, so that's an application of how we use gases to power our daily lives, or how we just live out or get around and travel. Okay. So they can also expand. So for example, if I have this flask here, and and I want to I connected to a gas inlet here. The gas inlet will fill this container with air or some kind of gas. It doesn't have to be air, okay? And if we stopper it, eventually the gas will pervade throughout all the space, because we know gas molecules, they're not attracted to each other. They're not very much attracted to each other, so they like to kind of go their own way, and they tend to move independently of each other without any influence on other gas particles. So we can't say that for liquids or solids, right? Because they tend to clump together and stick together. But the forces that hold the particles together in a liquid or a solid are not present here in a gas, so they tend to fill up their container completely. So it assumes the form of a container or whatever the vessel is, and if it's open to the atmosphere, gases will escape, and they will no longer have a fixed volume. Okay. So some examples of this are gas particles spreading through the room, like kitchen smells, very delicious food smells, bad smells, such as rotten eggs, spoiled food, or natural bodily gases. So they're all gases. They move very fast, so we perceive them more than something that doesn't give off gas, like water. So water's not very water doesn't really smell like anything, but it doesn't have a very high, what we say, vapor pressure, so it doesn't really generate water molecules in the gas phase at regular temperature. So we usually don't perceive a smell. And usually things that are very liquid and don't have low vapor pressures, they don't tend to emit gases as compared to volatile substances like some organic compounds, or like sweet smelling compounds, or bad ones. Okay. All right. Lastly, let's talk about volumes of gases versus liquids and solids. So volumes of gases, they tend to occupy more space than liquids and solids, just because they're freely moving, right? So example, 1 gram of liquid oxygen at its boiling point has a volume of 0.894 milliliters. Okay, so that's not very much, right? So that's less than water. However, the same amount of oxygen at room temperature and atmospheric pressure has a volume of 753 milliliters. That is an increase of about 800-fold. So that's a lot of volume. So that's why when you bring liquid oxygen to boil, it'll occupy a lot of volume. And if it can't occupy this volume, it can lead unto, if it's trapped in a very fragile vessel, it can potentially burst the vessel. So let's say it was in a very small glass container and you measure 1 gram in there. Eventually, if you heat it and there's no way for the gas to escape, it's going to explode. Okay, so we have to kind of be careful when we're working with gases, because usually if you have something that's naturally gas at room temperature, oxygen is definitely a gas at room temperature given by its very low boiling point. So when it turns into a gas, it's going to be a very spontaneous or very exothermic process. A process that's going to come with it a lot of chemical energy, or in this case, physical change, or physical energy related to the physical change. Okay. So when we do these changes in volume, it kind of comes in the form of energy, and we use that to do work. So work energy is where you use a chemical reaction, and that energy generated does some action on another process, just like the combustion engine. The combustion energy did some will use to turn the wheel, or will use the power or turn the wheel in your car from the engine. So that's the energy, that's the mechanical work being done in a car. made possible by a chemical reaction from combustion. Okay. All right. Another example is the steam engine, which brought about the industrial revolution. It uses water that boils to form a gas, steam, and steam occupies a much higher volume. If you ever thought about steam forming in a shower, um, it doesn't tend to stick around in the bottom of like a bath or shower box. It tends to like go upwards and escape. So it likes to occupy a larger volume. So when we do this, the pressure generated, generated can be compressed and do some work for mechanical work. And so the steam engines or steam baths, so that's what it's usually doing. Like you generate steam, that's usually heat something or used to do work on something, and that's what we call mechanical work. Okay. Another very risky, I guess, or maybe exciting example is when a dangerous liquid becomes an explosive. So nitroglycerin is also used in. If you Google nitroglycerin, you'll see some like formulations of it. So it's not just used for explosives; it's also used for formulations. It can be turned into solid form, by absorbing onto some clay or sawdust, and then when you light it, it'll just go off. So it's used in dynamite in like mines and quarries, to blow up rocks. So in case you want to mine ores, so this is why mining is so dangerous. You're breaking the foundation of rock, and then mines they can collapse, and miners can get trapped and end up suffocating under the rock because there's a lack of oxygen flow going through buried rock. So, but nitroglycerin is used as the source for dynamite. But usually nowadays, dynamites are pretty much only used if you want to destroy rocks. These days, but it was discovered by the Swedish chemist Alfred Nobel. So he's also the man who was responsible for the Nobel Prize, who the prizes are named after. So it's actually a chemist. So that's pretty cool. Okay, so when dynamite is detonated, it decomposes. If you look at this chemical equation here, you're generating over 3 times as much amount of. It's not even 3 times, like. So it's what, 22, 28, 29. That's like almost over 7 times more moles of gas. And these gases, they occupy much more volume than the liquid nitroglycerin. So when this happens, you're going to generate a lot of pressure, gas pressure, and that pressure, when ignited, will basically blow up anything in its path. So it's a very exothermic reaction. Generation of gases, when you generate a lot of gas like that, you're going to build up a lot of pressure, and that's going to be a very dangerous reaction. So that's why we see them kind of as explosions. Okay. They occupy volumes that are 100 times larger than a mole of liquid, so it's going to be several times more than that because of the amount of moles you produce. And the result is a shock wave. So it just happens like snap a finger, or like not even a snap, but probably like less time than that, like sub-seconds or maybe sub-milliseconds. And it's basically a energy bomb that blows up anything in its path, or that destroys anything in its path. Okay? Alright, so similarly, let's go to a more maybe more friendly example. On a smaller scale, this phenomenon also occurs when we pop popcorn. So maybe you never thought of how popcorn pops, but basically what happens is the kernel, you have some liquids in there in the kernel that will pop, or basically burst open to form popcorn, because the volumes of the gases the volume inside the kernel is very small. So when they get boiled to gases, they're going to want to escape, and that escaping is in the form of now a popped kernel, or what we call the actual popcorn. And that's how pretty much we use these concepts of gases to convert something you can't really eat the kernel. I mean, you can eat it, but it's not as good. And then to something like delicious snack like popcorn. Okay, so the volumes of the gases, they will want to occupy more space, so they escape by bursting open the kernel, and you form the popcorn here. And they probably just change shape because of most of what's inside the popcorn or inside the kernel. And it takes the form of this physical, softer physical form of the popcorn, which when you started with, it was just a bunch of kernels wrapped in probably butter. Okay. All right. So that's an example of how gases and volumes, how much volume they take, much more than their liquids and solid counterparts. Okay. So now let's talk about pressure and force. So another property of gases is the pressure they exert on the surroundings. So like when you put pressure in something like a bike tire, you can measure the pressure exerted by the gas on the walls of the tire by inserting a pressure gauge, or just inserting a bike pump or a tire pump, or any kind of air compressor gauge, or something with a gauge and that you can add air. So it'll tell you the pressure of the pump, and you can modulate the pressure by releasing it or adding more in case your tire pressure is too low. Okay. So as long as the volume and the temperature are kept constant, the pressure inside a tire will increase. The pressure will increase. So for like a tire, an actual tire on a car or a bike, you feel more pressure because to a point the volume stops. The volume doesn't really change in the tire. What changes is the pressure, and the temperature is constant, right? So when you're putting air in a tire, usually the temperature stays the same. And usually the volume stays the same. You don't really see the volume increasing on the tire like when you put air in a balloon, helium. So the pressure is pretty much increasing as you put in air or take away air. The pressure decreases, and that's why you can feel the tire feels more deflated, right? So what we can say is that pressure is proportional to the amount of gas in something, right? In a container or vessel. So the higher the pressure, the more amount of gas is in the vessel, because a lot more gas molecules are hitting the walls of the container, and that makes the container feel like, you take a water bottle, it feels hard. Sometimes it's not easy to compress when you put the cap on, and that's because there's an air molecules in there. And what you're trying to do is trying to compress the air in there, but the air has no way to escape, so you're going to feel the pressure bouncing back from the air particles. So the air particles are essentially stronger than you, unless you can overwhelm the air particles and pop off the cap, squeezing it hard enough. Okay? All right, so here, so then we can conclude, we can also define pressure in a different way. It's exerted on an object. We say it's the force divided by the area. So the pressure, the gas particles moving and hitting the surface, that's called a force. And when we have a specific force per area, there's going to be different kinds of pressure. Okay? So pressure is measured in units of pounds per square inch. So let's consider this example. For example, where a nail is applied a force by a hammer into a piece of like plywood, right? So you never you never hammer a nail on its end, right? On the tip or the point. And that's because there's less pressure, so you won't be able to, nail two boards together or nail connect two fences using this a nail here, or securing a fence, or maybe a construction project. So you tend to hit the nail on its head, right? Because if we think about it, the contact of the contact between this nail here on its head has a much wider area. So if we have a much wider area, that's going to decrease the pressure, right? Because area is in the denominator. So if area is larger, pressure will decrease. So if we decrease the area and minimize it to a single, like a point, that will decrease the area tremendously. So that will make this area very small. That's why in this top scenario here, when you hammer the nail, you have more pressure on the pressure. There's going to be more pressure experienced by the board from the tip of the nail rather than the head. The force is the same because the hammer, which carries the force transferred to the nail, is the same, right? It's the same weight. It's probably going to be this. It's going to have the same effect due to gravity, so it's going to carry the same force. However, when you hit the nail, the area experienced by the area of the board is going to be different. Or sorry, not the area of the board, but the area from the nail that's hitting the board is going to be different, and that's what contributes to a stronger force. Sorry, a stronger pressure, not force. Okay. So this is the basic conclusions I just stated. So the pressure is different on the wood, but the force exerted is the same. So the force does not change. Okay. Okay. So let's go over this example. Let's calculate the pressure exerted by the shoes of a 200-pound man wearing size 10 shoes if each shoe makes contact with an area of the floor that is 20 inches squared. Okay? So here we know pressure equals force over area. Okay? So we could say, since he has two shoes, the pressure of a single shoe would be only 100 pounds, right? Because the pounds, we would assume the pounds is distributed between both feet. So we're going to say 100 pounds. And still the area is 20 inch squared. Okay, so this would equal a pressure of 5 pounds per inch squared. Okay? So now let's compare that to a different scenario, and we'll pick that up in the next video. Okay, so see you soon.